to unified conferencing.
Is there anything else on the board?
No. Second cyclization precursor. It's might be the most beautiful at Mars right now. Like this was finally one show it to me tomorrow.
That's where they're
What?
usually
But it's like
They
it's
capped
really
the glass not this first like the neck.
yeah, that's true.
I mean, to be fair, 18
I can't really choose the thing to
Yeah.
exchange for gas. Yeah, because they exchange the CO.
Hey, TAs, we owe them 10 minutes, right? Is that right? Okay.
I asked me about it.
Okay, 8 o'clock. Hey, Florida, can you hear me? Good, great. So we have to finish indoles, and as part of that, we need to do a few more case studies, cover a few more name reactions, cover a few more strategic oddities, and then we'll get into, of course, radio labeling, and then we'll get into as-indoles, and then finally we'll end with some truly astonishing case studies of medchem versus process that defy normal retrosynthetic logic. Okay, great. So problem today number 8. I guess we can have a brainstorming here. The Floridians are welcome to join in here. I'll label some bonds that might help you.
Can you adjust the camera?
And we're looking for some suggestions on how to disconnect this. And maybe let's put 6 here. Elena, any thoughts on a good bond to break? You want to break, sorry, say that again, which one? 4 and 5. 4 and, okay, let's do that. So in order to realize Elena's disconnection, we need an oxidant, something to deprotonate, right? And then we need some sort of mustard. So we dip into the Department of Defense's remaining supply of World War II chemicals. And that's a good alkylating agent. In fact, you do see some people using this still to make pyperidines. Okay, because these things make aziridines and C2. I mean, that's why they use them during the war. They're pretty good killers. But they're also good alkylators. And then after that, we have to reduce the oxindole down to the indole. So you just need a way of making the oxindole. And it's just indole, so that shouldn't be a problem. Simple oxidation. There's nothing wrong with that disconnection. However, we need optionality because the people in your interview may say, hey, Elena, we really don't want to deal with mustard gas. And we also don't want to do that reduction. oxindole reductions of pain. And it may necessitate a very careful selection of what protecting group we can use at the NR position of the mustard. Any other thoughts here? Zhang, you got another disconnection for us?
My disconnection is actually almost the same as the Lang's.
Okay. I mean, there's nothing wrong with Lena's disconnection. On paper, it's fine.
Yeah.
It's just, we're trying to get you ready for the interview.
Would disconnecting 2 and 6?
2 and 6 sounds good. What kind of things will disconnect 2 and 6 for us that we learned yesterday or the day before?
Some kind of coupling, like
Some sort of coupling. Like what?
like along the lines of like Larock type.
Okay, so Larock type, let's do the 2-6 disconnection and use, palladium logic. That would get us down a road that looks like this. We would do an intramolecular HEC, and then we would reduce the olefin that we get, and we reduce the oxindole down as well. Is there another 2-6 disconnection that we have at the top there that doesn't use any metal? Yeah, why can't we just do that? And that's what they did. Fischer, and then in situ, reduce, because the in situ product you get is that imine. A lot easier to reduce an imine, by the way, than an oxindole. Reducing oxindole is usually, you want to avoid it. You can do it, but... Hey, there's another disconnection. Any other thoughts?
Just take orthofluoronitrobenzene and the related pipicholic acid.
And add what, Pavel?
The related piperidine or carboxylic acid or some derivatives or nitriles.
Okay, that makes the... And then you need something else here, right? What Oh, okay. Yeah. Mm-hmm. Great idea. And then reduce down? Sure. Only problem with that is that SNAR is not so easy because you're making a quaternary center. You might be able to do it with the, maybe the halide and then use palladium. That would also work, but there's nothing wrong with the disconnection. Certainly you put that on a test, we can't mark that wrong.
This would be kind of silly, but can you do like an interrupted pigtail spangler?
Aha, an interrupted pigtail spangler.
Because I don't know how you outcompete migration though.
Well, let's talk about migration. Migration implies that this could come from ring contraction. And that route would lead to making that beta-carboline, it's called. And then you treat the beta-carboline with something like NCS. And the thing will rearrange to can reduce. And then you need a good way of making that.
This is the last one we haven't talked about. You can also make the bond between 3 and 6.
Let's do 3 and 6. How do you want to do that, Saul?
I mean, there's 2 bonds you can think of. One is making the benzoic carbocation from a benzoic tertiary bromide.
And what's going to be the nucleophile there? Some tin species?
But the other one is going the other way, going into an aminium.
But then you need some good nucleophile there. You're gonna have a hard time with that nucleophile. But let's just do 3,6 here, just so everybody knows what we're talking about. That's what you mean? Yeah. I mean, so you could lithiate, ortho, you could trap with the ketone, and then you could alkylate with the tin species, and then treat that with some sort of acid and get it to close.
You do like a decarboxylic arylation analog, and then the hemiaminal, which is, make the amine, and then reduce.
So the Madelung disconnection is again 3,6. Is that what you... Okay. And then you want to...
So cut 2,6 and 3,6.
Oh!
2,6 is the decarboxylic arylation, 3,6 is the Madelung.
Okay, let's draw that. I mean, there's no reason to go into the how we arylate. Let's just say we get this bond, and then treat this with strong base. The only issue is the tertiary anion. So it's debatable whether that's going to work versus just easily deprotonating here. I would be worried about competitive deprotonation here through like Peter Beek type chemistry. So you'll notice as we keep discussing this, the roots get more and more bizarre. But it's great that you guys have all these ideas. You need the optionality. I mean, if you can go to an interview and put everything we put there on the board, I can guarantee you get the job. Very simple. That's what they want to see. Okay. How about this intermediate from Lily? Let's... Now, we discussed a reaction the other day. Didn't go through exactly how it works, but a reaction that's really good for making C7 substituted indoles. And so when you see a C7 substituted indole, it's often good to think about this type of reaction. But anyway, let's talk about some ideas for a disconnection. Tanner, any bonds you kind of just want to get rid of right away?
Can you break A and indole?
Wonderful. Let's get rid of it. Bless you. Okay. Makes it simpler. 7-member ring is gone. Lucas, any general thoughts on this indole? Almost anything you say I can use. Do a substitution and put the which one? Put the what? Put the chain coming off? Okay. So if that's a great suggestion. So if we disconnect DC, that's what you're saying, Lucas? Yeah. If we disconnect DC, let's look at the predicament that puts us in. Or let's say you put a bromine there, right? Is that right? How do I make that? Essentially, the question is, have you simplified my life? Probably not so much, right? It sure is fine. You might get there. You might muddle your way through on the test. It's fine. But you're just delaying the answer to the problem. And so this is a good exercise for us to go through, because if you make a disconnection and it didn't really get you much better off when you started, let's go back again and look for another powerfully simplifying disconnection. Sorry?
Bartoli.
So if you see C7 substituted indole, and there's no offending functionality, as Max says, a good thing to remember is Bartoli. What does Bartoli do for us? Well, Bartoli is CH functionalization logic. And the use of that logic is that it simplifies your life tremendously. So what it allows you to look at is now think about, this is just a reductive emanation away from becoming this group here. We'll just put that as a protected acetal. And when you treat with like 4 equivalents of vinyl magnesium bromide, you get out the product. This is a good reaction for medchem. You will never really use this for a process. I saw a company try to use this many, many years ago, and the whole time I said, this is insane, don't do this. Eventually they stopped, but they went pretty far before they realized this is not smart. But for medchem, it's awesome. Super, super chemistry. The yields are often pretty bad. Yeah, it's usually maximum. If you get 50% on the Bartoli, it's a good day. But 50%, that's like open up a treasure chest of gold for a medchem. How does this happen?
So Grignard addition into nitrogen.
And then what?
And then you get to nitro, so think upon addition of Grignard. Yeah. Okay, then another Grignard comes in.
Now I need Nick's help, because I don't know how to pronounce the next reaction.
Which one?
Well, no, I don't want Nanitsky. Give me the other one. So what does that look like from the pyro lecture? What does that remind you of? We talked about a way of taking oximes and acetylene and heating them with base and out pop pyrols. Remember that? And it was a Russian name.
Oh, the Trofimov.
Yeah, the Trofimov. Apparently I mispronounced it. I still don't know how to pronounce it. But Nick, can you say it real loud?
Trofimov.
Trofimov. Okay. This does a 3-3. Trofimov style. And you get out your product. And if you count the intermediate, just like the Trofimov, it's a 1,4-dicarbonyl. That's how Bartoli works. So that's why you need so many equivalents of the Grignard, because some of them are just reducing the nitro. Quite wasteful. Questions? Yeah.
Yeah, so naive question. For the problem with process scale is what with this? Is it like the exothermic in the Grignard?
So much excess of the Grignard. So many little byproducts that are difficult to remove. And yeah, when you're doing process chemistry, you're caring about the stuff which is like barely you can see in your NMRs today. That's what they're worried about. 0.1%, that's a bad day for them. And you can imagine a reaction that gives you 50, 60% yield always. That's the best you can get. And you've got 40% junk. And then you've got several kilos of magnesium waste to get rid of. That's hell.
Does this reaction typically work with these type of fluorides? No.
Fluorides are no problem. Fluorides, even bromides are fine. You can even do it with bromides. The key thing is, with a Bartoli, if you looked at the report card for indole synthesis, if you notice, they're really best yielding only when you have something blocking ortho to the nitro. If you don't, you start getting regioisomeric mixes, and it becomes far less useful. So that's why I say, if you see a C7 substituted indole, think Bartoli. It's kind of like when you see a C5 substituted hydroxy, you think Nenetscu, which I also don't know how to pronounce, apparently. What is it? Nick, what is it? Nenetscu. Okay. Right, that reaction.
You have an erroneous formal charge, by the way, floating.
Oh, sorry. So,
Bottom right, there's a plus where there shouldn't be a plus.
oh, sorry, yeah, thank you. Great. Any other questions?
So if you're in process and you make a C7 substituted indole, what do you do then?
Well, it depends on the context. Do you want to just focus on this one here?
Sure.
Okay. Yeah, it's a great question. So let's imagine we need to make this exact compound. Let's just do that one on process scale. What are the options for you? Well, you could think about substitution of the aromatic nucleus, but that's probably not so logical because you don't want to put fluorine in there on scale. So it's probably going to be logical when you see a fluorine in your aromatic ring, you want to buy the fluorine. So let's buy the fluorine. And then the first thing I would sci-finder are things like Leiden-Gruber-Batchko. So I would think about let's see how easy that kind of thing would be to make. The other thing I would think, since you have a C7 that's totally a C7 substituent and the other ortho position is totally free, obviously, then you could just do a simple Friedel-Crafts. And that just comes back from the aniline. That's probably the way to go. Just treat this with acid and you'll get your product. There's nothing else to do. Wouldn't do Fischer. I would just do this. That amine is definitely available. Any other ideas? That's what I would do.
Wait, so you did the Friedel-Crafts before or after the benzodiazepine exposure?
I would do the Friedel-Crafts before.
Okay.
I mean, the benzodiazepine is, I mean, I guess you could, it would be trial and error, but it seems like a good bond to make at the very end. But maybe towards the beginning you could put it there. Certainly, yeah. Either way. Yeah, good question there, Steve. Okay, more brainstorming. Problem with it, number 9. So we need, Alex has, I noticed him raising his hand in Florida. That was great. Thanks, Alex. So problem of the day number 9, A, would be great if you could help us on some bond disconnections here. And yeah, I started you off. So what do I do, Alex?
Probably disconnect N and C2. And
Okay.
maybe also 3 and 3A.
And then what?
Well, I'm going to make the indole like Larock type or Castro indole synthesis.
Larock type, or what was the other one?
Castro.
Okay, yeah. So using some sort of palladium alkyne chemistry. What's the only thing that, might not be the most fun to do at the very end? Putting the methyl in there.
Yeah.
And we'll see this again later. This is a very medchem way of thinking of throwing the methyl in there from a CH bond. You could do that through bromination and then Negishi, right? But another way to look at this would be to break this bond and then think about it's similar to a Leiden-Gruber Batchko, but more appropriately called a Reisert reaction. There you go. So the Reisert reaction is just you make the anion here, you quench there, and then you just reduce the nitro compound and it cyclizes shut. And you've got whatever substituent you want here. This can be anything you want. This is super acidic. You've got these 2 electron withdrawing groups. So that CH2 is ready to be deprotonated. And that's a Reisert. Nothing wrong with what Alex said. Certainly reasonable. Okay, how about this one?
No?
Yeah.
Can you do this Hammetsberger right from acetophenols, not from benzaldehydes?
No, those are not. I mean, there's probably a couple of examples in literature for that, but it's very rarely ever with a substituent to do Hammetsberger. Hammetsberger, remember, is the one with the azide here. That's what Pavel is saying. But very rarely do people do that. More likely, they would do what Alex said, which is to target this, make this through Hammetsberger, and then methylate. And then that comes from the aldehyde. Nothing wrong with that disconnection either, by the way. It's fine. If you want to do Hammetsberger to get there.
You should also go from the isonitrile and then trap this CO2. Like, so we have the ethyl compound, and then where the amine is isonitrile.
Oh, deprotonate the isonitrile and then quench that with CO2. You know, I haven't seen that. That might be, it's an interesting idea that Max has.
Yeah, I've always seen the example where it's like the methyl there. I haven't seen with ethyl, but might be.
Yeah, it's an interesting idea. It's reasonable. Deprotonate and then that will then cyclize on the isonitrile followed by quench of CO2. Yeah, it's clever. Mm-hmm. Hey, Chang, what's up with this? What's this? It's a protecting group. It's a good protecting group for 2 amino type amidines, guanidines. When you see these types of systems, this is a really robust protecting group that you can just remove at the end, and it renders all of your compounds nice in silica gel. So that's good. And what would be the conditions that would allow us to forge the indole ring onto that? Tucker, any ideas on a reagent you might use? You can use a cheat sheet if you want, the laminated sheet. It's a name reaction. We talked about it before.
It's a Basho line.
Yeah, great. So you essentially need to add 1 carbon and have that carbon be in the aldehyde oxidation state. And the reagent you're going to use for that is going to be what? So there's DMF-DMA. And that's the product you get. And then treating that with palladium on carbon gets you down to the amine. You're at a 1,4-dicarbonyl, after all, and that's just an indole or a pyrrole hiding. Oh, sorry. There's your 1,4-dicarbonyl. Now, when we see a ring system like this, as we will talk about in, I guess, next month, we have this question of where do we start from? In this case, it's kind of obvious because I've given you your starting material. But there will be cases in the future that we'll see where it would be more logical to make a pyrrole and then annulate onto that a pyrimidinone. So stay tuned for that. How about a quick solution to C? Yeah, sounds good to me. Look how easy this is. Done. Even with the bromine there, it's not a problem. How about D? D is a very tricky one. D is for deep thinker. Where is the deep thinker here? Second row max looks like the candidate for D.
Right. So it's going to depend on what I can buy.
All right. What are you thinking about? What are you going to look in? What I want to know is what you're going to look up in SciFinder.
I think I could probably buy the carboxylic acid.
Carboxylic acid. Where? Let's label these. 1, 2, 3, 4.
Right. So I'm breaking 4, 1, or 4 with the nitrogen somehow.
Is that what you want?
Yeah, I'm not sure how I would make that bond.
Well, I mean, if you but what you've done is clever. You've done some sort of CH functionalization act, and so if we want to recapitulate that, maybe we could just do what Pavel said before, which was just do a Hemmetsberger, and that would get us down to going to SciFinder and looking for ways to make that. With the idea we would Hemmetsberger it, we would decarboxylate, and then we would oxidize up to the isoton. Does that sound like fun to you? A lot of steps. You're looking at probably at least 8 steps to make that thing. It's a lot. What else can we do? What do you say, Nick?
Like 2, 3 and use Gassman.
Gassman, that sounds awesome. Now, Gassman gives which product?
So, side
Oh, yeah. You'll get your oxindole product out, and then you can oxidize it to the isoton. No problem. Not debating that. What I'm debating and questioning is, which way does it go?
So,
Uh-huh. What do you say, Cheng?
I think it's hard to say.
Hard to say. And I have strategically blocked you from larocking your way out of this question by putting the iodide there. Sorry. This is a typical consulting problem. They look simple, but they're, the consulting problem will come to you and it'll say, okay, we did the reaction, we did the Gassman, and it gave the one-to-one mixture of inseparable. We need a way to get only one. That's what it looks like. What's that? I said they're inseparable, even with their best analytical department.
Can you block the other position?
And if they need, like, let's say for MedChem, they need 10 grams of that scaffold because they're going to do Suzuki's or Buchwalds all day. Sorry? What do you say, Tanner?
Block the other site, the other nitrogen site.
Somehow add another substituent here to help us along our way?
Yeah.
It's getting complicated. What do you want to put there? You've got to put something removable that doesn't destroy the iodide. The iodide is blocking you from a lot of blocking groups. And then if you want to put a TMS, how do you get the TMS there versus next to the CF3? Or versus going to the other position of the iodide? It's difficult to do directed metallations with iodides on a benzene ring.
Could you use the fact that it's more acidic next to C3 and deprotonate?
More acidic? You're sort of some sort of directed metallation. It's a lot of guesswork.
Could you put the iodide in later?
Can you say that, Steve?
Put the iodide in later?
Put the iodine later how?
The CH functionalization.
You laugh at him now, but that's actually not a bad idea. So if you Now make your target this. Or it can be the isotin, whatever you want. Either one, guys. You can oxidize it, and then. So how do you do the CH functionalization there?
Meta functionalization.
You don't need meta for this one. Where's the where?
C6 iridium borylation, and then
Just do an iridium borylation, which you know on a 1,2,3 substitute aromatic always goes para, always goes away from all the stuff. It's sterically guided. So you just make this isotin somehow, and then CH functionalization there. I think that's pretty good.
Vicarious nucleophilic substitution if you start from the nitro using Valibert.
To make this, you mean? To make that?
No, to make the target.
Well, if you do VNS, again, you have to worry about where it's going to go. And the strong base of the VNS might give you benzyne. Right? I just don't know. If you put a nitro here and you do VNS, you can attack here or here. Do you know which one it's going to go? Same problem. And so you can, during an interview, sort of say, all right, I'm going to draw all the resonance structures for you and give you a quasi-DFT suggestion that convince you I'm going to get the right regiochemistry. That's not what they're looking for. They're looking for something that there's no ambiguity at all. So this one, you give the suggestion, I guarantee you get the job. If you're just looking for the one-to-one mixture, by the way, and you want to make an isotin directly, there is a reaction called Sandmeyer. The Sandmeyer isotin synthesis is worth being exposed to in this class. It involves taking an aniline, hydroxylamine, and chloral. And you get this intermediate. Which then with PPA will cyclize. And then lose hydroxylamine. That gives you, it's called the Sandmeyer isotin. But the Sandmeyer isotin synthesis won't help you for this problem because, again, you would get a one-to-one mixture if you started from the simple aniline. So it's no better than the Gassman suggestion. But just so you know, that reaction exists. Sandmeyer isotin synthesis. Okay, great. How about E?
can I Fisher with dihydropyrin? Or pyrin? Sorry.
This one, a Fisher with
Dihydropyrin. And then that alcohol that you get afterwards could be oxidized up to the acid. And then if you equivalent the nitrogen, you can do photocraps after the carboxylic acid is converted to nasal chloride. And then burn off the ketone. And then take off the
It sounds good. It's a lot of steps, but it sounds good. On a test, 100% credit. Except, what's the potential problem in your route?
C2 reactivity.
Uh-huh. We're going to have to stop that C2 reactivity. Any suggestions for doing that?
I think you could protect it. It goes as loose as C4.
Then you're okay. So you just throw some PG on there, maybe a Tazol, for instance, would be good. And then you may be good to go. They did not do that, although that's 100% credit on the test. They instead realized that this just comes from that, which you can reduce down and then acylate, and then treat with butylate, and you're done. So Madelung will also get you there. So the tetrahydronaphthalene, you can nitrate that, goes there selectively. So that's the kind of thing you would think about. You would SciFinder that building block. You would actually put into SciFinder just this. Then you would find there's like 900 vendors that sell that. And then you'd be like, okay. But if you didn't know that disconnection, you'd be in trouble. So the purpose of these problems of the day is strategically to get you to save time when you do SciFinder. Okay, we have to cover two obligatory natural product syntheses. And these are two of my favorites. They have some instructive value, which is why I cover them. And the first one comes from Fukuyama, the catharanthine synthesis. And the first disconnection is rather obvious. One just sort of does a SN2 alkylation to make that top ring. The next disconnection uses a very bizarre reaction that is a very useful indole synthesis. It's called, not surprisingly, the Fukuyama indole synthesis. And it involves breaking of this bond. And leading you to an intermediate like this. So this intermediate is treated with Lawson's reagent, which converts that O into an S, and then you treat that with tin hydride and AIBN. That tin radical that you form adds into the thiocarbonyl at sulfur, giving you a stabilized radical, which then undergoes a 5-exo trig reaction, and you then rearomatize by losing the tin S species. Okay, great. So now we have to disconnect this, which can be fashioned from two simple building blocks. And no one has caught me on that. So how do you suspect I'm going to be able to differentiate the two carboxys there? I've got to react that with this amine. I need a Woodwardian scholar.
One is exo and one is endo.
Okay, and?
So it should go to the exo one selectively, because the endo one is steric.
Well, how do I even make this? How do I even get this hydrolysis to happen?
I mean, the same way, right? Like if you assume that it follows the standard reactivity of that bicycle, it should always go exo over endo. Or you can, I guess...
Exo and endo relative to
Are
what?
you
If I
saying,
draw
like,
it the other way,
Are you
it's...
saying like cyclize one of them onto the olefin?
Oh, that sounds pretty good. I like that. So if you had this diacid, for instance, you could easily do some sort of temporary iodo-lactinization maneuver, which would then shield us from having to think at all anymore about the reactivity of that carbonyl. Thank you, Hannah. Perfect. So we would take this compound, we would iodolactinize. That gives us only this acid free. We would then couple to the amine. We would then de-iodolactinize treated with zinc, methylate, and then do your tin hydro reaction. Now we just need a way to make this amine, and it turns out there's a nifty way to do that through the deconstructive functionalization of quinoline, a byproduct from coal tar. If you take quinoline and you treat it with thiophosgene and barium carbonate, that's the product you get. Suggestions on what intermediate? What's the first thing that happens when you take quinoline and you treat it with? Back to lecture number 1, I think. And then some hydroxide is around to do what? And that's how you get that with the correct, with the olefin stereochemistry drawn. So a sneaky way of making that amine, the isothiocyanate can be easily dismantled, the aldehyde reduced, and that gives us the desired aniline we need here. We do our protection trick that Hannah taught us. We then make the amide, lawson, Fukuyama indole, done. Pretty good, huh? How about duochromycin? Obviously we need Gigi to help us because he's just finished going through publication 893 of Dale. And I think this is right around publication 402, so this is no problem. First, we're going to break the cyclopropane. Okay, great. And that actually has to do with the mode of action. Great. Now, Dale has multiple syntheses of duochromycin, as do many people. We covered one already when we talked about BMS's scalable approach to making this compound. You folks remember that? The BMS approach with vicarious nucleophilic substitution. We covered that in lecture 3. Now there's multiple approaches to this, but the one I wanted to cover, which I think is just the super prettiest, is the one that takes advantage of the inherent symmetry of this molecule. Do you remember this one? It's way before your time.
I think just cleave the two bond members by cleaving the next three bond. Yeah, because I remember it started from like
Brilliant, brilliant. All right, I will report dutifully back to Dale that you are now qualified to remain in his group. So these quinone diamines can be tuned by adding just base. You'll get attack here first. If you add a Lewis acid, you'll get attack in the other spot first. And so what they add is sequentially malonate at that position. And then after that, the equivalent of that. Now, this is a 15-step synthesis, so I'm really crudely summarizing this for you. But what I want you to do is trace out first, let's look for the malonate. The malonate is here. So the reduction has to happen. The malonate adds in a simple Michael reaction, and then you reduce it down to the diol. Here's one of your sulfonyl. There's one of your amines cyclizing there. Pretty cool. Your other one is right here. Pretty awesome, huh? It's not ultimately the best way he was able to put this together, but I think it's one of the prettiest out there. Questions on this approach? Very creative way of making this. Okay. We're required by law to cover radiochemistry. So problem of the day, number 10, takes advantage of everything you've learned so far to come up with routes that can selectively label with C14 at all the designated positions. So we'll start off with the easiest one there is, just C2 labeled indole. Dongmin, any quick answers for this one?
We can probably do the same trick we did last time, the oxidative.
Oh, you want to oxidatively open and then reclose, huh? This one that we learned the other day. It's possible. mean, certainly you can propose this on a test. No problem. Other ways that would get us there quickly?
Take orthonitramethylbenzene. We treat that with labeled electropotassium.
Great. What if I want, actually, radio-labeled DMF, DMA, or even DMF? It's totally usable, but it's pretty pricey compared to formic acid. Can I use formic acid?
Yeah, you do a first ring.
Can I do a what?
Like a first ring couple. So instead of methyl, have the aldehyde, and then take the amine and react it with labeled formic acid and acetic anhydride, and then treat that with titanium. Do like reductive carbonyl coupling.
This one?
Yeah.
That's certainly fine. What if I don't want all that titanium stuff? Madelung. That's probably cheap and fast, but there's nothing wrong with what anybody put here. It's all good. Can we use the same logic again? We've only put one hydroxy in there. Certainly everything has to hold true here. What do you say, Saul? You want to just do the same thing as before?
No, because you'll cause all kinds of garbage if you try to deprotonate an equivalent methyl. Because you make an orthoquinomethyl.
So we can put some sort of PG on here. Let's put like benzyl. And what do you suggest we do in that case?
If that's protected, then I think we can go back to a Weinberger-Botch's disconnection of the okay.
Certainly possible. Let me just show you what they actually did. Very clever. They went from here using a vicarious nucleophilic substitution. So as it turns out, for reasons that are more empirical than understandable, when you have a nitro group with a meta OAR, or OPG, the vicarious nucleophilic substitution prefers to go in the middle rather than going here. And so you deprotonate this, you add in, and then reduce with palladium on carbon, it gives you the product. This is derived from a simple SN2 of the chloride and labeled KCN. If you put on a test what Saul said, there's nothing wrong with it. This is just giving you optionality. What do you say, Nick?
Is the selectivity high?
Selectivity is a 67% yield. So it's one of these observations out there in literature that is sort of matched across a variety of substrate classes. When you have the meta OR, the VNS reaction goes in between. Certainly don't expect you to know that. Aha, now C3. What do we do in C3? Yeah, what do you say there, Papa?
They used KCN or bromoacetic acid or bromocetonitrile to get this intermediate label.
Oh, sorry. I put my label in the wrong spot. Thank you. Sorry. Thanks. Sorry. How about C3? I mean, Pavel gave us a clue on what might be good on C3. Steve, what do you say? Keying element for a Nenetskew. We just have to get that thing radio labeled. And there are ways of making that thing. It's a little bit more pricey. But it's a reasonable disconnection. Bless you. It's just a very expensive disconnection.
How do you think they would make it?
You would just take this compound. This would just come from and your label is right there. So you can get labeled methyl iodide, make the Grignard from that. I've seen them do that. So methyl iodide is okay. And then add it into the oxalate. So it's reasonable.
You can formulate annually and then
Emmetsburger, yeah. So you could make this from the corresponding bromide, for instance, then quench with labeled CO2, reduce, and then Emmetsburger it. All good suggestions.
Could you do that same kind of trick, but with the para-analyte, like a directed metallation, and then quench with CO2 and then condense?
It's a great idea. So directed metallation should go here. Quench with labeled CO2. And then we need to get to the finish line. How do you close the ring?
So if R was the other, that ester fragment.
Yeah, I mean, we covered this last on Tuesday or Monday. Somebody proposed this as well. These kinds of closures are possible, but just going to require an extra little protecting group there. So, no problem. Super. Yeah.
For DNS and 50, so there's an old literature saying normally goes to C2 because of cation binds to the nitrile group.
So there's a chelation effect?
Chelation effect. So if you run the action, for example, THF, make the tighter ion contact pair with European profile, selectivity diminishes. And for example, if you throw in a ground user, selectivity diminishes as well.
So there's a chelation effect here.
Here and nitrile. So
Bringing them together.
goes to C2.
Okay. Did everybody hear that? Florida, did you hear that? Thanks, Yuzuru. That's a way of at least rationalizing it. The next one is difficult because we haven't really learned about azindoles. So let's take a little detour for a moment and talk about azindoles. You know, when you look at an azindole, we've got two heterocycles embedded. And do you think it's in general what we learned basically in lecture 1 or 2? First, let's go back to first principles. Which ring is more aromatic? Pyridine is more aromatic. So based on what we learned in lecture 1, I think it was, we should therefore disconnect that one last. Right? Because if we go back to indoles, would it have ever been logical for us to make this compound? Nobody suggested we make this compound from a pyrrole and then annulate on a benzene ring, right? That was that would have been weird. Everybody's already just laughing at the hysteria of even trying to think about that. So in a similar vein, 80% of the ways of making azindoles, I would say in medchem it's going to be more than 90%, are going to be starting from a pyridine and annulating on an indole. That's why you need all the optionality of the 100 ways we learned how to make indoles. But process chemistry, it might actually be flipped. Often we'll see cases where it might be more logical to actually build the pyridine. Now, if you want a good way to sort of remember how to make as-indols, turns out there is a chapter in the book on this. So if you look on the screen here, there is your sort of rules of engagement. And those are the various types of as-indols. And what is an educational thing to do is to think about why we made these ratings. So you might go through these and wonder, why are some of them less recommended than others? We can take, for example, the case of Fisher indolization. So, Zhang, why do you think in the case of Fisher indolization, this may be less recommended? It seems rather stark contrast here. For 4 and 6, you're good to go. But for 5 and 7, it's sort of questionable. Why would you say that just based on first principles?
Probably withdrawing electrons from nitrogen.
Yeah, so that hydrazine you would make is probably not it's not a great hydrazine for making that hydrazone intermediate you need. And that's what they found empirically as well. That doesn't work super well for 5 and 7 for that reason. But this is the extent of the as-indol chapter for simple reason. That is, everything you learn for indols can be applied to as-indols. And all the ways we learn to make various substituents, we already learned on the pyridine case. We spent a long time on that, on lecture 2 and 3, how to functionalize pyridines, and the review session that David and Yuzuru gave you. Taught you everything you need to know about making pyridines. And so, when we get to the as-indol case here, we can look at this and say, you know what? We can just do the same thing here. So the answer to that problem of the day is simply with the exception that I would not recommend doing the oxidative cleavage. Because the oxidative cleavage is probably going to give you an N oxide on the pyridine. How often do you guys deal with as-indols over at Pfizer there, Patrick? They're pretty popular. We'll cover a few examples, but, I mean, they're great interview questions. And we have a surprise lecturer coming that I won't announce for a while, but when they do come, that person will likely talk about as-indol synthesis of epic proportions. How do you alkylate these things? Let's say you want to acylate, do a Friedel-Crafts. If you want to do a Friedel-Crafts on an as-indol, what do? Aren't you worried? You're not worried. Why are you not worried, Saul?
Because the carbocycles are really deactivated, but C3 is almost as activated as indol.
Well, doing a canonical Friedel-Crafts on as-indol is sometimes difficult because of the competing acyl formation. So what people often do to get these to go is use large excess of aluminum chloride to first chelate the nitrogen of the pyridine and then do the Friedel-Crafts. So there's a JOC paper published just on how to do that because it's not so straightforward. So there's little idiosyncrasies that you need to learn in terms of reactivity, but essentially everything you learned about making pyridines is going to help you in thinking about the pyridine component, and then everything you learned about indols is going to help you in how do you annulate from the pyridine onto the indol to make the pyrrole system. So as indols, it's a pyridine and it's a pyrrole, and they are great roommates. So we'll cover 2 here in the remaining 20 minutes or so of pretty epic stories in medchem. This first one comes from Bayer, and the second one comes from Merck. So for this first one, we need to think about some general ways of disconnecting. So it's an interview question. They threw this on the board. What are you going to say? How about Vincent?
Like to cut off the phenol.
cut off the what?
The phenol, so the oxygen bonded to the pyridine group.
That's your disconnection?
Yeah.
Okay, looks reasonable. The choice of X here is going to be NO2 in the real world. Now, what if I want to diversify my alkyl groups at C3? That's going to take me back to a disconnection we used way over there. I forgot who said it, but someone was recommending and we can throw a protected group on there. Putting a methyl in through a Negishi coupling, it's poor form. Unless you're in medchem. Why? Don't laugh at them. They're making drugs curing people. Not you guys, except Patrick. Oh, well, you're not doing it right now? All right, okay. Well, not everybody has billion-dollar drugs already in here. So, no, the point is, a med chemist is going to want to diversify, and so you may want methyl, but you don't know you want methyl. You have to look for propyl, butyl, isopropyl, benzyl, all of it. And so installing it at the sort of intermediate or at the end would be ideal in this particular case. So now all we have to do is fashion that, which we already learned how to do. Now the process people look at this and they say, that's pretty bad. We're definitely not going to be able to use this because we don't want to do Negishi at the very end. Any thoughts on how we might be able to make this on process scale? And let me say, I don't think in a million years, unless you've seen this paper already, you would guess how they did it. But let's just get your thought. Sorry, say that again? From aminopyridine. Okay. To aminopyridine?
Well, to amino for something pyridine. And the bishop.
Well, after we make the azindol, we can nitrate. In theory. You make the N oxide and then nitrate. So the suggestion here is to do some sort of Bichler synthesis. Do you see any potential problem with this? It's pyridine. It's not great. But in the case of pyridine, you might even have a competition between the nitrogen and the carbon in this case to make a type of heterocycle we won't cover till next month. Bridged heterocycles. Because you can imagine some sort of cyclization at that cation here or the Friedel-Crafts desired that you want.
Use the pyridone.
This? How do you want to make that?
Azamichael, and then addition into
I'm going to break which bond? This one or this one?
No, the other way. So
Okay. Yeah, I see what you're saying. Some sort of construct like this. How do we make that? Sort of a it doesn't necessarily get you back into a territory that you're super happy with, does it? What if I told you in the group at the time, at Bayer, they had a wonderful way of making kilogram scale quantities of that? Do you think we could use that for anything?
You can just reduce it by the method.
Can't hear you, Max.
Can you just reduce it by taking out the fluorines
Huh.
and adding nitrites?
That sounds pretty good. That's great. In fact, that strategy can be used quite often. For instance, a few years ago, BMS had an orglet on this exact topic, where you can take these, what they call anionically activated trifluoromethyl groups, because these are in the oxidation state of a carboxylic acid. And you can treat these, for instance, in ethanol with ethynolamine. And get these types of compounds by the same type of mechanism you just mentioned. So if we treat this compound with LAH, we'll do exactly what Max said. Why does this make our life easier? Well, because it should be a lot easier to handle the intermediates with the CF3, for reasons we'll show you in just a moment. Let's think about how to make this. Does it make sense to start with a CF3 pyrrole and build on a pyridine? Would you do that, Hannah? No. Does it make sense to make the same as indole and then do some sort of trifluoromethylation on scale? No. Is there a better disconnection? From lecture 3? Which bond might you break? What do you say there, Tucker?
2, 3.
We're going to break 2,3 eventually. Let's do it. Let's do it. So this is your 2,3 disconnection, Tucker. So when we do a Henry reaction and add in here, and then we reduce this palladium on carbon, it's going to close NB. Now I just need a way of making this. Lecture 3, what do we do to make that? Well, pretty good, right? Now in the forward direction, now they have a way to make metric tons of this compound. In the forward direction, we're going to make the N oxide, form the nitro compound, and then work up the reaction with a acid chloride or carbamoyl chloride of some sort, but you can imagine POCl3 is fine, and put the chlorine there. The purpose of the chlorine is it makes the SNAR much cleaner. The purpose of the CF3 is it's a protecting group for methyl. It makes the nitration take place much easier. As you can imagine, if you take a simple unsubstituted 7-aza-indole and you nitrate this, the competition is going to exist between C3 and C4. So having a methyl group there doesn't help the situation. You still get some nitration there because it's still electron-rich position. CF3 shuts it down. So they tried doing the whole route with a methyl there. Doesn't work very well. They tried doing the whole route with the unsubstituted. Obviously doesn't work well. The med chemists found that out. So they used CF3, which is a blessing in disguise. Makes all the intermediates nice and happy, crystalline, stable. All the reactions work better. The SNAR reaction works better. The nitration only gives one isomer. And then at the end, SNAR here, and then LAH, couple of equivalents. Reduces 1, 2, 3, 4, done. You may look at this and say, I don't like this synthesis. You don't like it because it's very, it's in defiance of retrosynthetic analysis. I mean, there's nobody who, if you didn't read the paper, nobody in this room, I would definitely would not, nobody would get this, that you would start from the CF3 there, right? The only reason they thought of it is because they had an ongoing program where they were making these in a different context, and they already knew they could make these. And then somebody came to the realization, wait a minute, that CF3 might actually be a good methyl group hiding. So a good process chemist, when you get the job, the first thing you should do is go back into the logs and archives of the company to find out what they did. Often my best value as a consultant is just telling them, 8 years ago you did this, and you probably have this intermediate sitting around in a stockroom somewhere. And they don't know. They're like, wow, that's useful. So I'm like just a human inventory person. So that's what you should do when you go to these companies. Check out what they did 10 years ago. Questions on this story? Okay. Well, last one. And it looks like we'll hopefully give you back your 10 minutes. Problem of day number 11. Medchem versus process. And a great segue to next week's series of lectures. So Vincent, again, I'm going to call on you again because you had a really good disconnection before.
So cut off the file.
Okay, let's just take off the file. And hopefully you can tell us some suggested conditions for that. And let me also emphasize that this is a medchem route. Suggested conditions for this?
I guess I need some kind of electrophilic sulfur, right? So maybe from the sulfonyl chloride.
Yeah, so either this or that. It's fine. It's nice and electrophilic. Should work fine. Okay, great. Now we're in medchem mode. But I need to simplify this further. We saw something similar to this, I believe, on Monday, this motif. How would you install that sidechain?
Mitsunobu.
They did it through Mitsunobu. Brilliant. These people did not do it through Mitsunobu, but guess what? The same intermediate applies. So what they did was a simple Horner-Wadsworth-Emmons followed by reduction. But you could easily do what we did on Monday. Just reduce it down and then Mitsunobu it and then decarboxylate. No problem doing that. But they did HWE, followed by reduction. Now, how do we make this thing? Which of the three rings would you like to disconnect to make your life a little bit more simple?
Do alkylation of the pearl-like nitrogen, and then that takes you back to a ricer.
Alkylation here?
Yeah. To make ring C.
And then what do you want here? But that's going to beta eliminate to a Michael.
So
Do an azamichael, okay. And then how do you make that?
Then you can get that from a ricer to make ring D.
Well, but I can't just carry the methyl vinyl ketone through that through the ricer step.
So install it through linear division and do a line random.
Great. What I'm looking for is this compound. And then we can argue about how we'll put that together. Let's get my isopropyl before I worry about what Steve said. So I'm in MedChem. How do I put my isopropyl? Can't hear you.
Can you cross couple?
Okay, that sounds good. I can do a silly, followed by reduction. You could do a Suzuki today if you want. And now I go back to Steve. What was the way you wanted to make this?
Ricer.
So you want to have a nitro and a methyl there? It might be commercial. Probably is. The way they did it was just this aldehyde, and then via Hemmetsberger. Okay, so to summarize, the MedChem route involves a Hemmetsberger reaction that needs 170 degrees in xylene, then a Stille coupling followed by hydrogenation, and then they need to forge this ring here, which they do through treatment with base and methyl acrylate. So you get first an addition into here. That then adds into here. That then gives you this, which upon treatment with acid, decarboxylates. The standard Dieckmann gets them to that. Dieckmann is a great reaction for MedChem or process. Great way to annulate rings. Following that, they do an HWE, they hydrogenate, and then electrophilic sulfur source. And this route relies upon the standard way you would think about making an azindole, which is pyridine first, then pyrrole. The process chemists did something miraculous. They looked at the same type of intermediate, right here, and they said, you know what, the last step is pretty good. The Dieckmann, that's scalable. The HWE is fine. We can do an asymmetric hydrogenation. The last part of the synthesis is great. The real problem of the synthesis is the first part. We don't want to do Hemmetsberger. We don't want azides. We don't want Stille. None of that stuff. The The problem is if you're wedded to make a pyridine followed by a pyrrole, you're always going to be relegated to these types of strategies. If you, however, think about building up the pyridine from scratch, everything changes in a dramatic way. Watch how dramatic. All of these bonds can be made through Friedel-Crafts reactions. Everything. Friedel-Crafts. 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 All of it. Let's start from the beginning. Last I checked, that's cheap. Methylchloroformate, pretty cheap. Isobutyryl chloride, pretty cheap. Friedel-Crafts is going to go, we already learned in one of the lectures. Right here. And then our last bond can be forged just by dumping in that. So Friedel-Crafts number 1, Friedel-Crafts number 2, and the third Friedel-Crafts takes place right there. Treat that with little acid. No need to isolate this. Is this route better than the other route? Sol?
That's what you're trying to do.
Yes, exactly. It's context dependent. You could say this route is far more efficient to get to the target structure. But if you're a med chemist, you could say this is a useless route for me. It's tragically useless. Because if I want to modify my alkyl groups at every stage, how am I going to do that with this? And I believe I'm giving you back at like 4 minutes. I still owe you 6, I guess. So any last questions? So next week, finally, we will get to how you actually make pyridines. But you see we did it here. That's our intro to pyridine synthesis right there. So next week we'll cover that ad nauseum. I would think it would be a close call, but if you want to try to get more of the bromo, add a little bit of copper. Not chloride. That's copper chloride. You're going to Suzuki?
Yeah. Are we able to make like the
Yeah, and that happens much faster with a bromide than a chloride, but that's a tough one. You likely would get a mixture, but if you want to stack the cards in your favor, try some copper. Copper chloride. There's a nice TED-led paper from her. So basically, this standard acidity conditions with 1 equivalent of copper chloride. You can try side by side, with and without. One full equivalent of copper chloride. You can try side by side, with and without, to see if the mixture changes. And also try to do it at 2 different temperature ranges. So first try it at 1 at 80 and 1 at like 30. And the other thing you could try is use the most advanced ligand you can find, like an S-phos, versus the standard plating tetraphase. So 6 different reactions would give you the answer if this is going to be tractable or not. You can always have 6 in parallel, 2 temperature regimes, 2 ligand sets, with and without copper. That'll tell you whether you're hopeless or whether there's some chance.
Yeah, thanks. What I was thinking is to, I guess, a more kind of along the way to store.
What does that become?
I make
Pyridone eventually?
Yeah.
Oh, well then just throw, yeah. I mean, so that's your backup plan. If you can't get any selectivity, then sure.
That would work.
No doubt.
The only problem is when I also have one another group here.
Okay.
And OPM usually
Oh,
have
okay,
base
yeah.
kind of the natural and the use as well. So there is base in this in the reaction current in our compound.
Yeah, just you mess up your
Yes, decompose it or something. Not sure what it does.
So you can stick with CF3 then?
So, well, the CF3 work, in fact, I think should work, but natural, I tried without the methyl and decomposed. With the base, we tried to protect the sun.
Yeah, so in that case, probably you'll want to try for the selective acidity conditions.
Yeah. Okay.
Yeah, yeah, sure. What's any mind?
I remember you saying something about using factors to reduce.
Yes. We'll send you the review. There's a nice review on it.
Okay.
Yeah. Do you have it? If you remind me, I got to run to a deposition, but it's the phosphonium chemistry from Johnson & Johnson to do.
I think it's in the book. Yeah,
It's in the book. It's in the book. But we
can pull it up. Yeah.
Okay. We'll send it to you, but it's in the book. Yeah. We love that chemistry. It's used a lot. It's super convenient. Yeah.
All right. Thanks.
Yep. Sure.
Also, I checked about the test is actually.
Still alive?
No. He was.
What?
Should we erase
Oh
it?
yeah, we gotta do that.
Okay.
Told you, I'm not recovered.
So do you guys still eat garbage for lunch?
I didn't go yesterday.
Okay.
I've eaten food that I've brought the last couple of days.
Okay, so it's real food.
No. I was curious if I thought
Okay. Another one in the books, huh?
Oh yeah.
One less lecture to do.